All right.
So we're going to talk about, I need to change the title there, radio building blocks. Amplifiers, a little bit about efficiency, and that's really the different classes of amplifiers. And there's some questions about amplifier classes on the exams. Oscillators, we have fixed and variable types.
Hey, are you sharing your screen? You got a slideshow?
Yeah, aren't you seeing it?
No, I'm just looking at your
Oh,
I'm just looking at your file.
it says I'm screen sharing. Well, let me stop
This
it and reshare.
It might have been the wrong screen.
See that one?
There it is. Got it.
Okay. Huh. I never will figure out this screen sharing thing. It works weird. Okay. Talk a little bit about modulators to do AM and FM and digital. In the second part of it, we'll do the demodulators and filters. So one of the most basic components or building blocks is the amplifier. And they still do make them out of vacuum tubes. The power amp I bought at the Hamfest is a 4 vacuum tube model that does 800 watts. Actually, I saw the guy doing a testing for it. He was over 1,000 watts PEP. Most of the newer stuff, and particularly in the radios, whether it's an RF amplifier or an audio amplifier, is going to be solid state. Usually some combination of bipolar and MOSFETs. And we classify the amplifiers essentially into class A, B, C, and D based on their configuration and their efficiency. A class A amplifier has the lowest distortion of all the amplifiers, but it's no more than 25% efficient, because whether there's a signal there or not, it's always consuming power. They bias it in the middle of the operating point, so it makes it very inefficient when you look at the power out versus the power in to the amplifier. The next one is called a class B, which they came up with to try to get the same kind of low distortion that you get in a class A, but increase the efficiency. And they do it by what we call a push-pull configuration, where you use two transistors or tubes, and one amplifies the positive portion of the signal and the other one amplifies the negative portion of the signal. So they're only on 50% of the cycle. The one problem with that is there's a little crossover at 0, which gives you a little bit of distortion, which is why it's not quite as good as a class A, but it's much better efficiency-wise. Then there's a class C, which is used normally in like an RF power amplifier. And you're using it for things like FM, or cases where distortion in the amplitude isn't really a problem. And they can get up to 80% efficient. They use a tuned circuit. So in essence, you're sending a portion of the waveform into the tuned circuit to cause it to oscillate and amplify the signal. And then you've got essentially a digital class D, which uses a pulse width modulation technique where it outputs a variable width pulse that's proportional to the amplitude of the input signal. And it makes it very easy to then filter that and recover the signal. But it allows you to use almost, in essence, switching transistors. So you get very high efficiency. They're either on or off. There's no in-between state. And we talked about efficiency, and it's just a measure of the output power versus the input power. I did an example here of my 7300 transceiver. If I set it to put out 100 watts, and it's on a 13.8 volt DC supply, it draws about 17 amps. So if you plug that into the equation, it comes out that it's only 42.6% efficient. In other words, you're putting 234 watts into it to get 100 watts out. This little chart shows the different classes and kind of the relative efficiencies.
What, just curious, just sidebar quick for Robert, what would be considered the main cause of the inefficiency? What's eating up the difference or the delta between output power versus input power on amps?
Well, can be a number of things. If it's a class A, for instance, it means that it's set at an operating point where it's always consuming power, even when there's no signal.
Okay.
Okay. So
so versus a class D, just so I pick up where you're going, is class D, it's a modulating system. So the modulation is what reduces the inefficiency or power consumption, right?
Because your active devices, your transistors, let's say, are either off, okay, at cutoff, or they're at saturation. So there's very little power dissipation in the device. It's either off or on, not in the middle, which is where a class A is.
Right.
Now, and we threw an AB in here. A class B, it's biased such that it's off for 0, and then it for the positive half. So you kind of get the average there, and then you got another device doing the negative half. Okay, so you've only got a device consuming power 50% of the time.
Right.
For a sine wave, or sort of a sine wave.
Okay. Just curious. All right.
And
didn't mean to take you down the rabbit hole on that one. I was just kind of curious.
And the questions on the exams, and I don't remember, I think there's something about classes on the technician.
Okay.
Definitely the general was. Well, true, but you basically need to know the relative efficiencies between those.
Gotcha. And that's standard is the output power over the input power.
Yes.
Okay.
Here's a typical class A transistor amplifier, which I did in circuit lab, and plotted the output. So you can see the input signal there in blue, and the output is the gold or yellow one. So it had a gain of what? We got about half a volt peak in and a little over 3 volts peak out. So about, well, in fact, up here it says gain 6. Basically, for the Class A, these two resistors determine the bias voltage on the base. And there's a little bit of a negative bias in the emitter resistor, but the combination of these determines how much current is going to flow from base to emitter, which establishes the operating point. And like I said, if this is what, 12 volts, you'd normally set this bias so with no signal, you're going to be sitting at about 6 volts at this point. So then when you put a signal in, it allows it to swing between 12 volts and 0 volts. But it's always going to be sitting at 6 with no signal. Same thing with doing it with a JFET. The only difference here is it's the bias voltage as opposed to the current. So it's whatever voltage you put on the gate element of the field effect transistor. It works the same way. In fact, this is just like the way you would set up a vacuum tube amplifier. It's also a Class A, so it's biased such that, again, well, it's 10 volts. So this would normally be set around 5 volts with no signal in. We also have what we call operational amplifiers, which are integrated circuits. It's an analog amplifier in a small package. A lot of them are in the same kind of package you see a digital integrated circuit in a dual inline. They have extremely high input impedance. In fact, it looks like it's an open circuit, essentially. They have a very low output impedance. They have gain in the thousands. And we can control the gain of it with a feedback resistor network as some sort of voltage divider to give it the ratio between the output and the input, which would establish the gain. Here's a simple, fairly common LM324. It's set up as a non-inverting amplifier. So we take part of the output, then we feed it back to the negative input. And this becomes a voltage divider. So the gain is going to be the ratio of the sum of these two divided by that should be R2. Yeah, that's a mistake. This should be R2. So we give you a gain of 3. And that's just a simulation.
Is that a typo then? That should be
Yes,
that should
yes,
be
that should be R2.
all over
R1 plus
R2.
R2 over R2. Actually, I think what I did, I labeled them wrong down here.
Okay.
Normally, this would be R2 and this would be R1.
Mm-hmm.
But basically, you take the sum of these two resistors, and then you look at what proportion of that voltage across there. So that's why it's the sum of these two divided by this one, the tap point. You do it slightly different if it's in an inverting amplifier, like here. And these are simpler. The downside is it inverts, which may or may not be a problem depending on what you're trying to do. But in this case, it's simply the ratio of R1 and R2. And these operate in the audio, very low RF frequency ranges, depending on the op amp. But they're extremely useful devices for things like this and making active filters, which we'll talk about later. All right, the next major thing are oscillators. And we really wouldn't get very well without an oscillator. It allows us to generate an audio or a radio frequency waveform. And like I said, we had two types. We have fixed frequency. In a lot of cases, they can generate sine waves, triangle, sawtooth, square waves. They can be either a inductor capacitor as your feedback elements, or just a resistor capacitor, or it can be crystal controlled, which is what you normally use if you want a very stable reference oscillator. And depending on how stable you want it, you might even temperature control that crystal, because temperature will affect the frequency of it.
Just real quick, Robert, what's the acronyms LC and RC?
Inductor capacitor, LC.
Okay.
And RC is resistor capacitor.
Okay.
We have variable frequency oscillators. A lot of times we refer to it as a VFO when it's in a receiver or transmitter, which means we can tune, we can change the frequency. And in the old days, that was done normally with a variable capacitor that were plates that would, one set would rotate and mesh with the other. So it would allow you to control the amount of overlap of those plates, which varied the capacitance. You don't see that much anymore, unless you buy an old antenna tuner or something like that. It might still have variable capacitors in it.
But that mag loop antenna that Byron gave me, the tuner for that, I think is.
Yeah, I think it is. Most of the VFOs that you're going to see in modern radios is going to be done with a varactor, a variable capacitance diode. So you're using a diode in reverse fashion and taking advantage of the fact that there's a capacitance across that diode junction, and it varies with the reverse bias voltage on it. So it allows you to use it as a voltage controlled variable capacitor. So you can just tune your transmitter or receiver with a potentiometer, or in some cases an encoder that's varying the resistance. In a lot of cases, particularly in SDR or software defined type radios, you will see what we call direct digital synthesized oscillator, which is based on a fixed crystal oscillator with a feedback loop around it and a variable oscillator, so you can generate variable frequencies with the precision of a crystal oscillator. It's done essentially digitally. I think there's a slide a little later on showing more about that. But essentially, for like technician, you just kind of know that you've heard of it. And then we also have in the digital world, clock signal generators, which you use to basically control digital logic circuits. They're usually all run off of one or more clock signals, a timing signal as a reference. And that's usually done with a crystal controlled fixed oscillator. They actually sell them in small packages where you just apply a voltage and you get a square wave clock signal out of it. Okay, to make an oscillator, there's a old saying that if you want to build an oscillator, you build an amplifier, and there's a good chance you'll have enough feedback that it'll oscillate. So all an oscillator is an amplifier with some negative or some positive feedback that's frequency dependent. In other words, if you wanted to have an oscillator for a megahertz, you would feed back part of the output of that amplifier through essentially a bandpass type filter set for, or I should say a tuned circuit set for that frequency to feed it back to the input and cause it to oscillate. Now, the real trick is for it to start and sustain an oscillation, you have to have an overall loop gain of 1, which means the amplifier has to have enough gain to compensate for the loss in the circuit and result in a gain of 1 on the total circuit. If it's less than that, when you apply a voltage, it'll start kind of like ringing and then go down to 0. If it's too high, you sort of get the opposite effect and it goes to whatever the high voltage state is. So it's really kind of critical to get an oscillator circuit just right. And in a lot of cases, you'll need some sort of variable element so that you can have a higher gain to start it, and it allows it to operate at a lower gain. This is one of the one of the names that you'll need to remember. There's on the amateur radio exams, they only talk about 3 types of oscillators, even though there's dozens. And these are probably the most widely used, and other ones are based on them. This first one is called a Colpitts, named after some guy named Colpitts. The key is whether or not this is an op amp or a transistor or a tube. The feedback element is going to be this inductor and capacitive divider resonant circuit. So you're going to take the output, feed it through this tuned circuit, which is half of its reference to ground, back to the input. The other one that you'll hear about is called a Hartley, again after some guy named Hartley. And you notice that we've swapped the components. Okay, the resonant circuit is now a voltage divider or a tapped inductor and a capacitor. So one way I remember, Colpitts has the capacitive divider. So C for capacitive divider for Colpitts. So obviously then the Hartley is the other one.
Can you snap back to the Colpitts real quick?
Sure.
Okay.
So it's the same circuit. It's just
Yep.
The tape circuit's different.
Gotcha. All right. Got it.
And then the other one you'll hear about is the Pierce, which is essentially a crystal oscillator, where you've got a piezoelectric crystal as the feedback element. And this operates at or will resonate at a specific frequency. And they actually manufacture these to 2-3 decimal points. Can make them very accurate. And normally on a piezoelectric crystal, it may require some capacitance on either side. It will depend on the crystal, but normally you'll see a circuit like this and you'll have some small picofarad values. And as we talked about piezoelectric crystals, this is the equivalent circuit. Now I know this doesn't come up on the technician, but definitely the general or the extra, where you have to know the equivalent circuit.
Yeah.
Because one of the questions is about this parallel shunt capacitor. You need to know the definition of this, but not for the technician. It's essentially built as a slice of a quartz crystal that has metal plating on two sides of it in some kind of holder. And as you apply a voltage, it will cause that crystal to expand or contract depending on the polarity. And that will cause it to oscillate if you send it a signal in sync with the frequency it wants to oscillate at. And that equivalent circuit that you see is just simulating, if you think of this like a tuning fork, where you've got some mass, which is represented by the capacitance. You've got some stiffness in it because of the metal, which is the inductance, and then there's some loss, which is the resistance. Now, there are other types of oscillators other than the Colpitts and Hartley and Pierce. This is a fairly common one. It's called a twin T, and there's kind of two feedback elements, one with a shunt capacitor and series resistors, and the other one with series capacitors and a shunt resistor. And the purpose is to feed back out of phase the output signal back to the input signal so that it will oscillate. And this is what I got when I simulated that circuit. And you see, initially it starts off at a much higher voltage and then settles down to its normal oscillation, if you got all the values right. It took me a long time tweaking them. This is showing how to do it with an operational amplifier. And I actually had to use, and this is I don't know if they use it that much anymore, an old technique where you use a small, what we used to call pilot lights. Old radios and stuff used to have little like flashlight type bulbs to provide the lighting. Well, these have a variable resistance. They're low resistance when it's cold, just like a normal electric light bulb, and the resistance increases as it heats up. So you've got a variable resistance in there, which allows you to have a variable gain in the circuit. So it can have higher gain when it starts and the right amount of total gain when it is oscillating.
It's incandescent, right?
Incandescent, yes.
Okay.
Or something equivalent to that would have the same variable resistance.
Right. There's a transponder that we work on at work. we do mods on it for the FAA. Because they use it in a testing lab. So like, once we do our mod on it, it can never be put in an aircraft again unless it's modded back to its original status, because there's some things we take out of there. But that transponder has a lamp in it that none of us have been able to identify what it's for.
Probably to provide a variable resistor.
I'll have to look back at it now.
One of the other more popular things in this, the old 555 timer IC has been around for 50 years.
Yeah.
Probably. It's a little integrated circuit that is like magic. You can do all kinds of things with it. One of the main things is you can build a square wave oscillator with just a couple components. And this potentiometer over here allows you to control the frequency, because it's a this resistor capacitor network. So it works on the time constant, how long it takes to charge this capacitor up to a threshold voltage. So as you vary this resistor, you can control the amount of current going in to charge up the capacitor, therefore the amount of time it takes, which allows you to control the frequency.
Okay, so R8 controls the frequency.
R8 and 10, but yeah, R8 is the variable. It's a combination of these and the capacitor,
Okay.
which is the time constant.
Somewhere or another, I saw a drawing where you could use a 555 to make a CW oscillator.
Yeah,
So you'd have to have a key input to it.
right. You
Like, we've got units.
well,
that
I
have
mean,
been-
the simple way is just put your key,
Right.
okay, between the trigger input and this point here.
Oh, okay.
Okay. Now, it's not going to be a very good one because it might vary the frequency a little. You might have like a chirp,
Right.
but as far as practice, it would fine.
Yeah, that's what.
Yeah. And it just takes one little, what is this? 8-pin dip.
Yeah.
I was thinking it was smaller than that, but I think it's 8.
Yeah, I think the 555 is 8.
And they even have a dual one, 556, I think.
Yeah, the 555 is it sets up switching frequency in the KG 102. It's a heading gyroscope.
Okay.
And we've got a locker full of them that are deemed unrepairable that may have good 555s in there, so you can see where I'm going.
Oh, there you go. Oh, they're fun to play with. Oh, you need a little breadboard. Okay. The next thing we need to have is, or deal with, is modulation. So we need a modulator. Just generating a signal from an oscillator is nice, but it doesn't convey any information unless you turn it on and off like you do with CW. The fact that the carrier is there or not there. And that's actually a form of modulation. In this case, it's amplitude modulation because you're having the amplitude go from 0 to whatever the max is to send a CW signal or Morse code. For normal AM voice, okay, you're going to modulate it with a voice signal we call baseband, and that will vary the amplitude relative to the amplitude and frequency of the baseband signal. A special case of the amplitude modulation is called single sideband, where, morning, Ernie. when you generate an amplitude modulated voice signal, you get the combination of the carrier signal plus an upper and lower side, what we call sideband, which are equivalent to the baseband signals, shifted in frequency. So one is slightly above the carrier, one is slightly below the carrier. You get that by doing the cross product of the two frequencies. And if you multiply the math out, you'll see that you get those three frequencies out, the carrier plus and minus the baseband signal. Most of the energy in the standard AM signal is going to be in the carrier. Like we said, there's no information really in the carrier. It's in the sidebands. So in single sideband, what you do, and the two sidebands are mirror images of one another. One is inverted from the other frequency-wise, but it's the same identical information. They're just inverted copies. So all the information that you really want is in one of the sidebands. So for single sideband, we eliminate the carrier and we eliminate one of the sidebands. So if we were going to send upper sideband, single sideband, you'd filter out the lower sideband and eliminate the carrier. So all of the energy that you're sending, all the power, is going to be in that upper sideband fairly narrow signal. And we'll talk a little bit more about how you do that. The next one is frequency modulation, where you vary the frequency relative to the amplitude of the baseband signal. It gives you a much higher quality signal. It's more or less noise free. I just recently saw a little thing on YouTube or something, a demo back in the early days. It was a demonstration of the difference between FM and AM. And they set up one of these Tesla coil generators, putting out multi-thousand volt sparks, and had it operating, and then set up an AM and an FM transmitter and receiver. And all you heard on the AM radio was just a roar, and you could actually clearly hear the FM with all that lightning discharge right next to it. So that's its main advantage. It tends to be higher bandwidth, so it takes up a little more bandwidth, and it's normally used in the VHF, UHF range. You ever use FM at HF?
No,
You can though, right?
yes,
But nobody does.
not to my knowledge.
Okay. The next form is phase modulation, which is essentially the same as frequency modulation. It's generated slightly different. It's actually easier to generate phase modulation than it is frequency modulation. The ear, from what I understand, you can't tell the difference listening to one or the other.
What's just curious, I mean, they give examples obviously of, you know, AM, FM, and even, you know, spread spectrum, but what's a good application of phase modulation for communication?
Type they use a lot.
Teletype?
That's using multi-channels in the same band, 3 kilohertz bandwidth. They were using phase modulation for each little channel.
Oh, okay.
That's how Collins come out with that back in the 50s.
I would say today, most of the phase modulation is in what we call phase shift keying for a lot of the digital modes. Like there's one called PSK 31, which is used uses phase modulation.
Very narrow bandwidth.
Very narrow bandwidth. It's 31 hertz. It's even better than CW.
Yes.
And then there's spread spectrum, which you're probably sort of familiar with. That's what your cell phone uses. Most radio control stuff nowadays is all spread spectrum. It used to be FM at 72 megahertz, but I think that's just about gone. Okay, here's at the top is what we call our baseband or message signal, which is in this case a nice sine wave. Doesn't have to be. We have a carrier. If we modulate the carrier with this message signal, and mathematically all we're going to do is the cross product of the two, we get a waveform which looks like the one at the bottom. And this blue line is what we call the envelope. So in the receiver, what we need to do is detect that envelope, okay, to recover the message signal. Now we talked about single sideband being a special case of AM. And when you generate AM, you get a lower sideband, an upper sideband, and a carrier. For single sideband, we use a technique, usually a balanced modulator, which does not generate the carrier, just the two sidebands, and then we can filter one of them out. This picture is a suppressed carrier double sideband signal, which I guess in some cases they may still use, but I'm not sure why. Because the information on the sidebands are mirror images of one another. It's just a duplicate. There might be some case where you'd want to do it for reliability. So if you couldn't get one sideband, you could get the other one or something. I don't know. Frequency modulation, we've got our same message signal. We got our carrier, but we're going to change the frequency relative to the amplitude of the message signal. And we normally do that with something we call a reactance modulator, where its frequency, we can vary the frequency versus the input voltage. Another case where you could use a varactor, a voltage controlled diode, capacitor diode. Now, phase modulation, we have our same message signal, we have a carrier, but we're going to change the phase of the carrier relative to the amplitude of the message signal. And you get some weird looking thing like this where you're shifting. Normally, this is, or in most cases I've seen, it's done in digital modes. So your message signal is going to be a digital square wave. So you're changing the phase in increments. It may be 2, 4, 8. I think I've seen stuff go up to either 16 or 32.
Yeah, it's interesting just kind of looking up applications of just phase modulation, and I didn't realize that Wi-Fi predominantly, your Wi-Fi services predominantly use phase modulation.
Yes.
Wi-Fi, yeah, wireless internet signals use phase modulation.
Right. And then we also have, besides phase shift keying, we have frequency shift keying, where instead of shifting the phase, we shift the frequency, kind of like FM. but it's normally done in the digital mode, and we tend to call the digital signal, let's see, really uses marking space, right?
Yeah, mark space.
Radio teletype, which is RTTY mode, uses this frequency shift keying. So a mark or a digital 1, okay, causes one frequency, and a space a second frequency. So you get, you just either detect one frequency or the other. It's fairly easy to do a detection circuit. The other one up here, audio frequency shift keying, is slightly different. And that's what modes like FT8 and FT4 and some of those, I'm not sure about JS8 call, but FT8, for instance, uses what they call audio frequency shift keying, where it will generate an audio signal. Let's say it's 1500 hertz, and then there's 8. It's actually a 3-bit encoding, so there's 8 possible frequency states, 6¼ degrees apart. So it's 0 to 50 hertz. In addition to that offset, and that's generated by a computer, and that signal is used to modulate the waveform as opposed to just straight shifting the carrier. So it's actually similar but different. And as far as I know, the audio frequency shift keying is only used in a couple of the digital modes. Let's see, this is, comparing. Ooh, what's ASK?
It looks like I changed the amplitude right now.
Okay. I'm not familiar with that one. It's not my chart. So we have a digital pattern up here, 1010, and the carrier. So for audio shift keying, or amplitude shift keying, I should say, we're either increasing the amplitude or decreasing it. It's kind of like Morse code. Frequency shift keying, the 1 is going to be one frequency, the 0 is a lower frequency. Usually, could be the inverse. And then phase shift keying, you can see here is a drastic 180-degree phase shift. Guess it's 180.
Looks like it.
Says low speed data. SK is low speed data.
All right. Any questions on that one?
No, let me perfect that last.